the organizers for giving me this opportunity to describe Özden's life and work. And I'd also like to pay tribute to Shabir, who had hoped to be here today but can't be, for establishing the IRM in the first place. This seemed at the time like an impossible dream. Well, as you see from the title slide here, the best meetings are always the small ones. This took place on Margarita Island in Venezuela. It was the first Latin Mag meeting. I think it was 2008. Obviously taking a little time out from the sessions here. So I'd like to not only talk about the milestones in Özden's life and career, but also take you on a short photographic journey to begin. Then talk about her main achievements in titanomagnetites, soil and sediment magnetism, low temperature oxidation, even argon 4039 dating of magnetite, domain structures in magnetite, magnetite at low temperatures, and then hematite, her final fascination. Özden was born and raised in Turkey. She graduated from Istanbul University, one of the oldest universities in the world, established in 1454. I always like to point out that was the first thing the Ottomans did after the fall of Constantinople, was to establish a university. She then attended Newcastle upon Tyne University. Then that was the hub of paleomagnetism and tectonics for the whole world, really. She returned to Turkey fairly briefly at Istanbul Technical University, which is sort of the MIT of Turkey, but immediately took research leave at University of Minnesota right here. This was her first big international experience, and she had a very productive year at Minnesota. When she returned to Turkey, she became rapidly disenchanted with the military regime of the time and emigrated to Canada. After a year, she came to Toronto, and we held on to her firmly until her retirement. Her service includes being secretary of the GP section of AGU and a member of the IRM's Review and Advisory Committee. Her passion in life was rock magnetism, as Julie has said. Her eyes would light up. But she had many other outside interests. Music, she played the mandolin, dancing of all sorts, photography, travel, our grandchildren, and her cat, Momiji. And that was her cat, not my cat. Momiji definitely knew the difference. So a few pictures. I found we have very few pictures. We don't tend to take pictures of ourselves in the lab or when we're working. This is one rare picture that I have. We had a lot of get-togethers of our group of graduate students and postdocs over the years. This was in the mid-1980s when Valia Shecherbakova, she's sitting next to Özden, was visiting. She also entertained at home for all of our students, so they got at least one square meal a month. Another get-together, this time we've moved on to the 1990s with a slightly different group of people. Wynne Williams should be here, but is missing for some reason. And then out in the field, we didn't always have bad weather, but somehow it happened quite frequently. This is on Georgian Bay, which is part of the Great Lakes in Ontario. And lecturing at one of the castle meetings, another very productive and enjoyable small meeting. This one was in Yabarina, 2004. In the audience at Yabarina with other people you may recognize. And here we are at Latin Mag. Oh, I'm sorry, it's 2009, not 2008. A very convivial meeting, as you can see, with Eddie Petrovsky at the left. We had very happy times at Latin Mag. A number of people have asked me about our dancing. Here we are. Suzanne, you remember this moment? One of her favorite occupations in the summer times was to hike in the Canadian Rockies, which actually we still did up until 2 years ago. Starting at Sentinel Pass. These are the Sentinels. We're up on one of the smaller ones. You can see the spike in the back. We never did make it up that one. Here in more civvies by Lake Louise. On the ice line trail, looking down on glaciers instead of up at them. Again, looking down, this is a particularly dangerous spot. We never came back to this one. Lake Oisa, a lovely little mountain tarn, and then our last visit together to Sentinel Pass back in 2017. I think that's it for the photos. Özden was an artist as well as a scientist. This is one of her little sketches. And her cat Momiji, on the right here, is expounding his ideas about Mars' magnetic field, with which I don't necessarily agree. Momiji had his own ideas, as well as knowing exactly who his mother was. Well, to get on to Özden's science, this is from Özden's first published paper back in 1978, while she was just a beginning student in Newcastle. It was the beginning of a whole series of groundbreaking papers on titanomagnetites of mid-ocean ridge compositions, TM60s, and their oxidation products, titanomaghemites, because on the seafloor, they oxidize very rapidly. Her meticulous data gathering is really astonishing in an era before there was any sort of automation in measurement. If you wanted to measure it, you made the measurement and you stayed there until it was done. Each of these 39 data points required a day's experimentation. In Minnesota, working in the forerunner of today's IRM, Özden showed that low temperature oxidation of TM60 makes it much more viscous. You can see at an intermediate Z value, oxidation index, it's hardly viscous at all. By the time you get to 0.8 or 0.9, it's extremely viscous. You can see it changing on a laboratory time scale. Not a good thing for magnetic stripes. In describing this and the work generally done by Özden in the lab, Shabir said that Özden would let nothing come between her and the results of an experiment. I can endorse that, having spent whole nights with her in the lab. And just on a personal note, this work was first described in a talk in Edinburgh at IAGA in 1981. That was where Özden and I met, and we happened to have successive talks. This was the old days when you climbed up on a stage, took out your chalk, and started writing things on the chalkboard. She was coming down, I was going up, and as we passed, I said, "Good talk." It turned out to be an effective line. We've been together ever since. Özden did many other things in Minnesota. When Shabir first proposed this study of Minnesota soil samples, Özden said, "You mean to say that dirt is magnetic?" And despite this initial hesitation, she went on to measure in great detail VRM on the left and many other properties of soils. Nowadays, soil magnetism is, of course, a science in its own right, but Özden was one of the pioneers in this subject, and I think soil magnetism was lucky that she decided to get down and dirty. So she was in at the very beginning. Özden became involved kind of by accident in lake sediment studies because Shabir fell ill quite early on in her year here. And Özden became a co-supervisor of John King's PhD research towards the end of that research. One result of John King's work was on the far left, this quite historic demonstration of the granulometric potential of chi-ARM over chi, ARM over susceptibility. And just a personal note, the day plot on the right the discredited date plot shows exactly the same information in a very nice, compact, easy to interpret font. So when she arrived in Toronto, she had her research program carefully in mind, and in '84 she began the first in a series of landmark studies of CRM. This one involved oxidation of TM60 in mid-ocean ridge basalts over millions of years. I mean, these were analogs, obviously, in the lab, but they were 4-day experiments. They were certainly long enough, and they ran all night as well as all day. So yes, we were in there at night as well. And the result that she found on the Zeiderfeld plot here, the original TRM is horizontal, so it lies along the up versus north axis there. And when the oxidation parameter passes 0.7, you start to see this deviant component, the CRM, coming in towards a vertical field, which would be along the up axis. By Z equals 0.9, that CRM is about as big as the remembered TRM. So that's really quite an astonishing ability to hold on to the original TRM signal in the face of massive oxidation on the seafloor. Other examples that Özden did of CRM work, this is a favorite of mine, this little paper in Science, where she compared very simple oxidation of magnetite to maghemite, but some experiments done in vacuum and some in air. And surprisingly, the VRM that was produced was almost identical to the CRM that was produced when she oxidized the material. So similar in its kind of Hopkinson peak here and its stability characteristics. You see, it's very, very stable, as stable as TRM itself. She then called this a CVRM, chemical viscous remnant magnetization. In fact, the editor of Science was so intrigued by this, I think that's when the paper got published. Something that's not often talked about or known is that between 1990 and 92, Özden worked in argon 4039 geochronology. I can tell people why afterwards. I won't go into it here. It was not by choice. But she threw herself into this work, and her very first paper was a breakthrough showing that magnetite crystals contain enough trace potassium that they can be dated. Now, the error bars you can see are much broader than they are for companion biotite samples. But the interesting thing is that the magnetite actually records in the minimum of this plateau the correct age, whereas the biotite does not. So it comes out with an age of about 1140 billion years, which is about the right age for Grenville metamorphism. Back in rock magnetism, Özden in the 1990s embarked on a long series of studies of magnetic domain structure revealed by bitter patterns, which show the intersection of domain walls with a polished surface. And these photos are absolutely the best that have ever been published for magnetite, and among the best for any mineral. The trick here is to section a crystal exactly along a 110 plane, which sounds easy, but it's not. This was the kind of thing that Özden could do. I could never have done, I'm sure. 110 is a magic plane because it contains two of the easy 100 axes for magnetite. And therefore you get these textbook Landau-Lifshitz patterns that otherwise you just don't see. So these are absolutely beautiful lamellar domains, terminated, you can see, by textbook example closure domains, only they're not textbook, they are real, they're real photographs. And in the interior of the crystal, quite complicated closure and spike domain sections. Now, they're more than just pretty pictures, because by looking at the width of the lamellar domains versus their length in this graph on the upper left, you can get the domain wall energy, which is not something you can readily measure, but it's something that theoreticians need in order to do modeling. And the value comes out spot on 10 to the minus 3 joules per meter squared. Used to be even easier. It was 1 erg per centimeter squared. That was really easy to remember. And of course, her photos also provided a nice cover for Cambridge University Press for our book. More detailed pictures done a couple of years later with Song Shu providing extra expertise on this, showing closure domain structures in detail that I think had never been seen before, with spike domains on top of the classic closure domains and a set of little spikes on top of this, the main spike domain. So everything you could ever want from the textbook, all in one section here. Then another 2 years passed, and Özden looked into the effect of stress on domain structures. So getting a little dirtier, voids in the crystal, imperfections of various sorts. The lines here, A, B, C, D, E, F, are gaps in the colloid patterns, which show underlying line dislocations. So first evidence that the dislocations really are down there and presumably are acting to pin domain walls. And in the 2000s, she moved on to looking at much smaller magnetite grains. These are inclusions within biotite. And here the patterns get much more intricate and complicated. You can see imperfections like a crack at the top, a little harder to resolve in the photographs. There's a point defect of some sort in the middle picture. And when fields are applied, this is a set of increasing fields, these walls bend, which they shouldn't do in magnetite. This creates a whole lot of demagnetizing energy. That shows just how firmly these walls are pinned by appropriate defects, that you can actually bend the wall and produce enormous demagnetizing energy. And we like to speculate that maybe their complexity is the very thing that gives rise to single domain-like regions, because after all, we wouldn't be in business as paleomagnetists if there weren't single domain-like behavior out there in our rocks, contrary to usual expectations. So I couldn't resist putting this in. That I still feel there has to be some bridging structure between single domain and classic multi-domain behavior, because all magnetic properties are completely continuous over this range as far as the data tells us. But vortex structures and single domain structures are highly discontinuous. You've got to get past that gap somehow. Low temperature experiments. Özden began these as soon as there was an NPMS available at the IRM. And as the people here know, we have been frequent visitors, in fact, yearly visitors. You just couldn't keep us away for, I think, 12 years. This was in the early days, an expression of the Verwey transition in magnetite, which clearly depends a great deal on the orientation of the crystal. If you put an SIRM in at room temperature along an easy 001 axis, you get an enormous expression of the Verwey transition. But if you put it in just in a random direction, the Verwey transition is still there, but not nearly so obvious. Another thing that you get in the high resolution plot at the top, or the large expression of the transition, is a little hint, just in one data point there, of the isotropic point, which is almost never seen in data at about 10 degrees above the Verwey transition. Here, I guess this was in a following year. I don't know the, it was year 2000, I guess it was published. You get a rather small change in the saturation magnetization when you go across the Verwey transition. It's about less than a 10% change, in spite of this enormous change from the cubic to the monoclinic structure. But the change because of the enormous anisotropy of the monoclinic change. The change in coercive force is enormous. Özden also looked at the my famous 4 submicron magnetites containing single domain to vortex structures. This is the first of the hallmarks of magnetism papers, showing what magnetism does to the Verwey transition. Very rapidly broadens it and ultimately suppresses it completely. I'll discuss these data in the next slide, I think. Whoops. There we go. Looks better in color anyway. This is the second hallmarks of low temperature oxidation paper, in which instead of coming with an SIRM produced at low temperatures, you start out from room temperature and cycle across the transition. And the hallmark here is this humped behavior that you see when these left-hand curves are enlarged. They're not quite so obvious on the left. You see the stoichiometric magnetite curve at the bottom with a clear Verwey transition. It doesn't take very much low temperature oxidation, just 100, 150, 200 degrees C, to virtually suppress that transition. But these humped curves seem to be diagnostic. Well, what about hematite? We have to get to hematite. Hematite, unlike magnetite, which has this lovely continuous decrease in virtually all properties, here it's the TRM intensity, as you go up in grain size, hematite counterintuitively goes exactly the opposite way, with the fine grains having a weak TRM and the large grains a large TRM. You'd wonder how that could possibly happen. I mean, these large TRMs are sufficiently large to make hematite a very viable source of magnetic anomalies on Mars. And these are, as you know, massive magnetic anomalies. So these are just some of Özden's data in the submicron range, and also she looked at single crystals. Everything is nicely compatible, both with Néel's single domain theory, which magnetite never is, and Néel's multi-domain theory, the dashed line on the right. So how can you produce this large TRM in a mineral which by definition is weakly magnetic, 200 times weaker than magnetite? This seems very counterintuitive. Well, that very weakness means that there's virtually no internally magnetizing field in hematite. And therefore, by applying a field of 50 microteslas over here, applying something like the Earth's field, you are practically at saturation. You are making use of the saturation magnetization of hematite. So that's why it works. And although the AF stability is not as large as single domain hematite, or else you wouldn't be able to demagnetize it at all, it's pretty respectable, and particularly after you've cycled through the Moran transition, which is the lowermost curve. This is more complex work. Özden got into a lot of experimental work about the memory of hematite's magnetism when you cycle through the Moran transition. And the real question here, since hematite at room temperature owes its magnetism just to a small canting of spins within the basal easy plane, and that completely disappears below the Moran transition when everything is pinned along the z-axis, and I do mean pinned. When you go below the Moran transition, how do you ever find the spin-canted moment again in its original direction when you come up to room temperature? You don't find all of it, of course, but you find quite a substantial fraction. In fact, if you start at 0.5 there and trace that back up, that is the room temperature SIRM. Its memory is a third of the original SIRM, which is pretty impressive for something that should have lost everything at low temperature. So our model, such as it is that there are regions that can be pinned away from the C-axis at low temperature, and these form nuclei around which the spin-canted moment renucleates on, warming through the Moran transition. And evidence in favor of this from Özden in this paper from 2008 is that by applying increasingly strong fields, you can depress the Moran transition. That is, you can hold the spins against their will in the basal plane below what should be the Moran transition. And the depression of the Moran transition is exactly proportional to the field. It's also interesting, this persistent thermal hysteresis in the cycling behavior of hematite across the transition. The width of the hysteresis is not affected by the field, so that seems to be intrinsic to the mineral. And in one of her final papers, 2014, Özden showed that day plot sneaks in here again. This was before it was completely discredited, to show that multi-domain and single-domain hematites are very neatly separated on day plot. Isn't that nice? I think that's really nice. Oh, and on the left, this is a compilation of data, about half of which in blue are Özden's data, showing that fine grain size has the same effect. It will depress and ultimately completely suppress the Moran transition. And then to finish off, in that same 2014 paper, which is really a massive effort, Özden did an exhaustive search of the literature. And when Özden did a search, it was exhaustive, believe me, she didn't miss much. Showing here that the coercive force has a nice peak with grain size, or around 1 micron or so, but the saturation remnants does not. It continues large right up to large grain sizes because of this lack of an internal demagnetizing field. So any little fields you've got left lying around will do it. That will saturate the hematite. I once had an experience in Japan where I had measured fine particle hematites, and I showed it to the big boss in the lab. He measured multi-domain hematite. He said, no, this is not hematite. I have measured hematite. This is what it looks like. Not realizing how different the behavior is between these two domain states. Of course, being in Japan, I agree with them instinctively. So to sum up, Özden was one of the pioneering experimentalists in rock magnetism. Her PhD research still forms the core of our knowledge about titanomagnetites and titanomaghemites of mid-ocean ridge composition. And she did look at other compositions, but this was the focus of her work. And maybe the most important experiments were those early ones at Toronto, where she showed that single domain TM60 grains, that's what you find at mid-ocean ridges, can withstand as much as 70% oxidation without losing their TRM direction. Without that astonishing tenacity, there would be no magnetic stripes. If we didn't have the magnetic stripes, would we even know about seafloor spreading and plate tectonics? We would not be in the era that we are. Özden was also a pioneer in soil and sediment magnetism, and even in argon 4039 research, although she did not continue this work. Her studies of magnetic properties, alteration, and CRM encompassed many minerals: magnetite, high and low titanium titanomagnetites, hematite, of course, goethite, lepidocrosite, and even siderite. By precision sectioning of magnetite crystals in 110 planes, Özden revealed domain structures in unprecedented detail, including their interaction with dislocations and other crystal defects. And I think her two papers on the hallmarks of magnetism still remain useful to everyone in the community who has to deal with magnetite, and we all have to deal with magnetite. And finally, Özden always said, the red planet, the red mineral. That was her slogan in her final years. She was absolutely fascinated with Mars exploration. She followed every development every day. So she devoted her final years in the lab to the study of hematite, the most stable of all magnetic minerals, well, almost the most stable of all magnetic minerals, whose low temperature memory all rights should not even exist. Thank you.
Thanks, David, for that overview of a really, really remarkable career.
I should point out that she was remarkable for being a woman in Turkey who established geomagnetic research there.
Yeah.
There were not many successful women in science at that time, and certainly not in Turkey.
Yeah. Do people have any questions for David? Bring the mic around.
It's more just a comment, really, a passing comment, just about one of the points you got up there, the sectioning magnetite crystal on the 110 phase. I tried to do this myself about 10 years after she went through this, and I went through, I don't know how many crystals I went through trying to either. I couldn't do it, I was ended up giving up and doing something else. I was always in order, she managed to get those amazing pictures, and I just couldn't beat it. I mean, that's my inability to cut this one problem, but yeah. I don't know how she managed it. Did you put I mean,
She did it without X-rays.
right.
The folks at Munich said, "Oh, of course." Victor Hoffman in particular said, "Oh, of course, it's easy to use X-rays." But no, she used reflected light just to off the 111 surfaces of crystals, and I don't know. She just had the magic touch.
Magic dust.
I don't think many of us do.
Questions or comments? I wore my tennis shoes so I can run just get as meters.
Thanks, David, for that wonderful overview. Can you say a little bit more and give the field some guidance about the pseudo single domain state? I agree with you entirely that there's a range of data showing continuous behavior. But what does the discipline need to do to kind of reconcile this?
Well, something clearly doesn't add up. The data look as though they're absolutely continuous. But I do wonder if the fault lies with the data. You know, we plot things without error bars. That's a particular grain size, but in fact, there are probably enormously broad grain size ranges. When Barbara Maher did her first study of very fine grain magnetites, everything dropped off in a single domain range, and it was because there was so much superpermanganate material mixed in with it. So it's just possible that things are discontinuous, but it's somehow being clouded by the data. If that's not true, if things are truly continuous, then I eagerly await the micromagnetic answer. The more you look into these more complicated working structures, the more strange and non-intuitive things seem to become. Your only comment on bridging.
Well, there is a disconnect. I think it's probably partly in the. I think it's partly in the samples. We don't have samples which are.
I think it's partly in the samples. Don't really have samples that are in the correct size range, which are truly non-interacting, which are essentially stress-free. So even with electron-fuel samples that people have made work with, they tend to be affected by some sort of stress between substrate and particles. So it's very hard, I think, to get these perfect samples to really test the theories. The electron-holography work that we just look at individual crystals seems to be very well in Magnetism models to bridging the gap up to the bulk.
Do you think rocks behave like the perfect models or like the messy, stress affected?
Well, the stress and the accuracy and the distributions are very solid.
Yeah.
But in the synthetic sample, the interactions would be a problem if you less.
Oh, sure.
Oh, is there online?
There's an online comment.
Oh,
And then
Hoping that Lynn will.
oh, Wynn's here.
Yeah, did you unmute and ask your question, please?
Yeah, sorry, I wasn't sure if I should be typing in the chat or unmuting my mic. I was gonna kind of, David, I'm sure you're probably expecting me to say, well, I think vortex structures probably are continuous in the magnetization because there's the kind of flower state, the twisted flower state, the vortex, the multi-vortex. You can get a kind of continuous behavior, but that said, I have to agree with you that there's still a discrepancy between experimental observations and what we can model. And I don't know what the answer is. I think the more we look at modeling highly irregular grains, multi-axial grains, we do get kind of closer. And as you well know, every grain that you look at for natural samples has dislocations and fractures. Even those beautiful grains grown by Franz Heider, you will remember, still had these screw dislocations, even the most perfect hydrothermal samples that you've ever seen. So the effects of stress on magnetic structures and whether those then go on to create lamellar regions or single domain-like regions, I still think there is something there that we need to explore. So although, of course, I'm very attached to my beloved vortex structures, I think you do have a point.
How about that?
So one last quick comment.
Yeah, thanks so much, Dave. I just feel sort of lucky to have been here for you running through this overview of her inspiring career and seeing the arc of it from your perspective. I guess I really liked how you sort of highlighted how lucky we are in terms of the phase of oxidation of TM60 holding on to that TM signal. I wonder if you all ever remarked the same in terms of your last point here, in terms of the low temperature memory of hematite, particularly being in Canada, where at Earth's surface you can cycle through the morass quite frequently at those high latitudes, which seems like we're pretty lucky in terms of recovering hematite remnants.
Sure.
Properties.
Don't have to go to Canada, you can see over here.
Thanks. All right, well, let's give a big hand again to David and